First of all, this diagram is a regular pentagon with a five-sided closed shape, like a triangle is a three-sided. Pent is 5, with all its diagonals drawn and all points labeled. So a diagonal is a line that goes from this point to the other points, but it has to go through the shape. So AE, this line right here, would not be considered a diagonal because it's on the outside of the shape. But AD would be considered a diagonal because it goes through the shape to another vertex. So how many non-overlapping angles are there? Well, let's find out. We got this one, 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 this one. There's a lot of them. Let's keep going. I'm just marking these so that we can come back and count them once we get to that point. Just a lot of them. Yeah, how many angles? But these are non-overlapping angles, right? Because none of these are split by any other angles. So let's go ahead. All right, so that's good. Now here's the thing, though. Is there's 10 triangles, right? So we'll multiply that by 3. But then this inside shape right here is also a pentagon. So that one has 5, right? So that would give us 30, but then plus the 5 from the pentagon gives us 35 non-overlapping angles. Because there's 10 of these triangles up in here, right? Good. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3 angles each. And then we got the pentagon. So we added the 5 right here. And we got 35 non-overlapping angles. There are groups of angles that all have the same measure. For example, angle DEG and angle AEF have the same measure. How many different measures of angles are there in the diagram? Use a protractor. I guess we could look at that. So here's the thing, is this angle needs to be, it would be, since it's a regular pentagon, by the way, this is the only reason why we can do that. All of these angles marked in red would be congruent or the same. So that gives us 1 ankle measure. And then all these angles on the other side of these triangles right here would be the same. And then we've got these angles right here in green. So this is 3 total different angles. And then we got all of these is the same. So what are we up to? 4. And that takes care of all the triangles. And then finally, we also have these ones from this hexagon, and the pentagon in the middle, which gives us 5 different measures of angles. Now we don't need to know what they are just yet, because we don't need to use a protractor yet. But if we did, we could find the angles, the measure of each one. Actually, looking at this one, these angles are also the same as the purples. So it looks like we have 4. That's nice. Now we'll get into the reason why those are the same here in just a moment. And some of you guys may remember that from, I think, lesson 3. What type of angle relationship the purple and the black ones had. So those ones specifically were vertical angles. They spelled it a little bit different than I did. But it doesn't matter. It's where we got 2 lines that intersect. Two lines that intersect form vertical angles. That's true. Vertical angles are pairs of angles that are always opposite one another rather than adjacent to each other. For example, angle EFG. Let's mark that one up. EFG, which is this one, and AFJ, which is this one. Those are vertical angles. Again, that's because they're opposite one another. They're through the vertice on those. Then we got these adjacent angles. Two angles are adjacent if they have a common ray or side and vertex. For example, angle, let's mark these up, EFG, so that's still this one, and EFA, that would be this one, are adjacent angles. Now those two also form a straight line, which we'll get into here in a moment, but for now they're simply just adjacent, okay? So they're just right next to each other. I mean, well, a lot of these different ones are next to each other, right? Like this one, EGD is adjacent to DGH. And you probably notice with adjacent angles that they always share two of the letters. Again, that's because they share a side. So in the diagram, they have at least 5 vertical angle pairs. Use a different colored pencil to mark each pair in the diagram. Let's just name them for now. So what do I got? Let's start with AJB, angle AJB, and angle FJI. That's a good one. And then we also have angle, I guess we did AFJ. So let's do EFA, angle EFA, and angle GFJ. Bam. Then we also need one more. Let's look at some different types here. So there is 5 of our vertical angles right there. All right, let us name at least 5 adjacent angle pairs. There's a lot of these, by the way. So, for example, I can say angle ABJ, and then that would be adjacent to angle JBI. Angle JIH would be adjacent to, there's 2 of them, 2 choices on that. HCD? Nope. So it's got to share 2 of those letters, right? So I'm going to say JIB. So AFJ, right here, would be adjacent to, again, we got 2 options on this. We could say JFG. That works. And what about another one? Alright, so there are 5 pairs of adjacent angles. Of course, we could find more if we wanted to, but this list will do. Then we got this other one. That seems to be the relationship, or what seems to be the relationship between measures of 2 vertical angles. Draw another pair of vertical angles below by constructing 2 intersecting lines and measuring the 2 angles in the vertical pair. What does this example support your conjecture? Vertical pairs are congruent, and here's kind of why up in here. Is if we draw a couple lines, doesn't matter what 2 lines we draw. If I look at this angle right here, and then compare with this angle right here, these 2 make up a straight line, which we'll talk about means that they're supplementary. But if I were to compare this purple angle with 2 marks right here to this angle right here, they also create a straight line. So this purple angle is a straight line with this red angle and also the thinner red angle. That's why vertical angles are congruent, for one of the reasons. So what this means is if I had a measurement on this one, let's say that was 140 degrees, then I would know that this vertical angle also 140 degrees. Bam. Alright, angle DGE on this one, let's look at this, that's that angle. And EGF right here. These are called supplementary because when we add their 2 measures together, we get the straight line up in here. Well, a straight line has exactly as it turns out, 180 degrees. So when supplementary angles are adjacent, you can see that they form a straight line with the two outside rays. Supplementary angles don't always have to be next to each other like this. Sometimes we'll draw them separately. Like we'll draw an angle right here, and then we'll draw another angle right here. And we could say that those two would be supplementary, okay? And then we'll give you the measures. You guys got to find the missing ones. Keep that in mind because we'll see that on the homework. Find and name at least 5 pairs of supplementary angles in the diagram. Use a different color to mark each pair in the diagram. Alright, so we're looking for any angle pair that will give us a straight line on these. So for example, I've got angle AJB, which is right here. And this would be supplementary with this angle right here, which is angle AJF. Bam. These are supplementary because they give us a straight line right here. So yeah, we got angle AFE and EF. Alright, so we do have our 5 angle pairs right here that give us supplementary angles. But I'm going to do 2 right now that are not next to each other, such as, let's use angle FJI. So that would be this angle right here. And I want to combine it with another angle that is like AJF, but I'm not going to use angle AJF. I will be using another congruent angle with AJF, such as angle A. Wait, hold on, not A, B. BJI. Which would, oh man, those 2 are next to each other. Let me use a different pair. Such as, instead of BJI, I'm going to use JIB. That's better. Yeah. JIB. So I combined it with this angle right here, which is the same as BJI, as it turns out. For each pair of intersecting lines below, find the 3 missing angle measures formed. Justify your answer in the table. All right. Let's look at angle CEB, which is these. That one is vertical with 116 degrees. So we're going to say that that one's also 116 degrees. Then we've got angle DEB, which is this one right here. And how do we find the measure of that one? Well, it's supplementary with angle AED. So in other words, if we add these 2 angles together right here with the purple one, it'd be 180 degrees. Well, we've already used up 116 of them. So I'm going to take 180 and subtract the 116, which will tell me what angle BED is, or DEB. So subtraction, I get a 4 up in here, a 6. So it looks like it is 64 degrees because they are supplementary. And supplementary is a long word, so I'm going to put sub. Alright, well, what about angle AEC? That would be this one right here. Well, this one is congruent to angle BED or DEB because it is vertical. So this one's 64 degrees. And vertical angles are always congruent. So we know that they are the same. So on this one, we got that angle CEA, which is this angle right here. And we can see that angle BED, or in this case they use DEB, those ones are the same because they are vertical. So this one's 91 degrees, and the justification would be that they are vertical. Alright, so this one's 90 degrees because it's vertical with angle CEA. Now if that's the case, yeah, 91 degrees, that's good. Because it also is 91 degrees. Alright, this one, let's look at angle CEB, which is this angle right here. Now if we look, this creates a straight line with angle CEA, which means that they are supplementary. And so if I want to solve for it, I'm going to take 180, that's supplementary, but I already have one of the angles is 91. And that gives me an 89 degree angle for angle CEB. So 89 degrees, why? Because it's supplementary with CEA. Bam. So there's the justification. Ankle AED, this one also is 89 degree because it is vertical with ankle CEB. So we have this ankle AEC, which was given to us in green radical, and that's 90 degrees, so I mean we could make it a 90 degree right angle mark. But then we want to find the ankle measure of CEB, which would be CEB, this one right now.
90 degrees.
Now what we can see is that AEB is a straight line, meaning that CEB is supplementary with AEC. Therefore, if I wanted to solve for it, I would take 180 degrees, subtract that 90 degree, and that will tell me the measure of ankle CEB, which also is 90 degrees.
So they're all just 90 degrees.
Let's find out. Now again, that's because it was sup with AEC. There we go. Now the other two ankles we'll figure out a little bit differently. For example, DEB is this one. But since it's vertical with AEC, we know that it's 90 degrees anyways. And then we also have this other ankle radical, which will be 90 degrees, but it is 90 degrees because it's vertical with ankle CEB. Alright, this one gave us an intersection right there, two intersecting lines, but then they kind of connected the outside points to make a quadrilateral. So let's look at ankle IJG. That's the one that they've already marked there. It is 129 degree right there. Now it says FJI, which is this ankle radical. Now if we look closely at these, we can see that they are supplementary. That didn't work out very well. Supplementary because they create a straight line. So if I want that ankle, I'm going to have to take 180 degrees. I need to subtract the 129 degrees. And then we see that it'd be 1 and then 51 degrees. Very good. So this one's 51 degrees because it is sup with IJG. Alright, there we go. Because it is supplementary with IJG. Well, then we've got this other ankle HJG, which is this one. HJG is this one right here. This one also is 51 degrees because it is vertical with angle IJF. Alright, then we've got this other ankle FJH, which is this one right here. This one is 129 degrees. Bam, there it is. Ankles are complementary because their measures add up to 90 degrees. Now again, these don't have to be next to each other. They can be adjacent, but they don't always have to be. We just need to know that two ankles add up to 90 degrees, and then we know that they are then complementary. It's a crucial word. So we have two types of relationships that we've talked about. The first one was supplementary, which is straight. It's the SS thing, right? Complementary, because it's 90 degrees, or it's right angles. See, there's the relationship CR. Complementary, right. 90 degrees, okay? So when we see complementary, we need to know that it's 90 degrees. So looking back, what is the sum of all the ankles in any triangle? Yep, 180 degree. Consider a right triangle. What seems to be true about the two non-right ankles in the triangle? Use the examples below or draw your own examples to help with your conjecture. Whatever, here we go. So for these ones, we're not focusing on the 90 degree ankles. We're just focusing on the other two. So if I took this 60 and the 30, what do I get when I combine these? 90 degrees, which is what type of relationship? Complementary. Yeah, these two add up to 90 degrees. Well, what about this 34 and this 56 business? Yeah, these two also would be complementary. Bam. Comp. That works. Well, what about this other triangle with this 81 degree and 9 degree business? Also comp. All right. So as it turns out, if we have a right triangle, like we do with these three, the other two angles will always create some kind of complementary relationship. They complement each other, which is right. Right angles. Complementary. Look around your room in right now, whatever. Find examples of angles in the furniture. There's no real furniture in here. Tiles, posters, etc. Can you see complementary angles? Yes, we can.
Lots of them.
They're all over the place. They're in the ceiling tiles and the bricks and the papers. There's some on the triangles right there in front of you.
The desk.
The desk. There we go. Yeah, desk.
Yeah.
There's a ladder over there, a microwave, some cupboards.
Why do you have a ladder in here?
They're all over the place. Can you see supplementary angles? Yeah, they're all over the place in the same places as it turns out. Can you see vertical angles? Yep. Right here in the bricks. Well, I guess not in the bricks actually. Let me take that back. Supplementary. Do we got stuff? Oh yeah, there we go. The ceiling tiles. There's supplementary angles. Draw sketches for at least 3 ankle pairs you find. Okay. This one's complementary stuff. Alright, well, there's a part right there where it's a 90-degree angle, but we can see the line go through it over there in the room, right there. And then there was, let's see, supplementary. That's a good one. So on the bricks, they're split like that, and it creates a straight line. And verticalness. So if we look at the ceiling tiles, we get this ankle and this ankle. They're right angles, actually. So those are also vertical. Bam. All right. Use properties of complementariness, supplementariness, and verticalness. Ankles to find missing measures. 2 pair of seesaws. Those are fun. Sit unused at a playground as shown. EGF has measure ankle 140 degrees. So EGF would be this one right here. And we can label that right now at 140 degree. So which ankle is vertical to EGF? On this one, it looks like it's ankle CGH. CGH, which is this one right here. What is the measure of CGH? CGH would be, it's vertical with EGF, so very good. 140 degrees. Name an ankle that is supplementary to ankle EGF. So I will be using ankle CGE. What is the measure of ankle CGE? Well, these two ankles, we'll mark it right here. These two ankles are supplementary. So I know I got the 140 degrees, and we're gonna subtract that from 180 because they are supplementary. And we can see that ankle CGE is 40 degree. Okay, because they make a straight line right here. If we're going to use that one. What is the measure of ankle HGF? Well, this one is vertical with CGE, so it also would have the same measure right here. It also would be 40 degree. In this diagram, ankle ADB is a right ankle. The figure is formed by 3 intersecting lines. Fill in the measures and justifications in the table. That sounds like a great idea. Ankle ADG, which is these, right here. We need to find that ankle measure, but we don't need to because we can see that it is through the vertice with this 24 degree ankle. Therefore, it is vertical with ankle EDF. Bam. There we go. Angle GDB, that is this ankle, right here. Now this one, we don't have any verticalness with this one yet. We could, but here's the thing is we get to know that this ankle ADG is 24 degrees because it was vertical. But we can see that ankle ADG and ankle GDB are complementary, so they add up to 90 degrees. So I'm going to take 90 degrees and subtract the 24 degrees from ankle ADG. And that will tell me the measure of ankle GDB. So it looks like it is 66 degrees right here. Bam. All right, what about ankle BDF? Let's identify that one. BDF, that would be this ankle, which also is a supplementary because it's a straight line with ankle ADB. Now ankle ADB is 90 degree, so if I want to solve with these, I got to take 180. We already used up 90 degrees on here with this ankle ADB. So that would give us 90 degrees for ankle BDF. Since that is 90 degree, we'll remark this using a right ankle marking. All right, finally, ankle EDC. EDC is this ankle right here. Well, this one is vertical with ankle GDB, so it'll be also 66 degree.